here again.
Okay, right. So I'm Spencer Becker-Kahn. I'm an unestablished lecturer here in DPMMS, Department of Pure Mathematics and Mathematical Statistics. And I just started the start of this term in October.
So one of the things you're interested in your research are so-called minimal surfaces. What are minimal surfaces, and can you give us an example of one?
Yes. I'll give you the example. So I'll try and tell you what they are. Then I'll give you the example. There's probably two things I would attempt to convey to describe what minimal surfaces are. So the first is a related notion of an area minimizing surface. It's an accident of history that the terminology doesn't refer to the same thing. So to understand an area minimizing surface, let's imagine I just draw a circle here in front of us, and we can think of different ways of filling in this hole with a surface, like a nice thin sheet. So one way to do that would be a completely flat, sort of taut surface stretched across the hole. Another way to do that might be to have similar surface, but it sort of bulges out a bit like this, like an upside-down bowl. So both of these are surfaces that fill in this hole, as it were. So at the boundary, at the edge of the surface, is that same circle. But the flat, taut one has less surface area than the one that bulges out. So in fact, that flat sheet that forms that flat disk would have the smallest surface area out of any surface that you use to fill in this hole. Okay, so we can say that that flat disk is the area minimizing surface for that boundary. And so that's a very important notion. These somehow are, if you like, the things minimal surfaces are made out of. So a minimal surface is slightly more general in that it might be some big surface in which any small part of it is an area minimizing surface. This is a slightly more difficult thing to get one's head around. There's one analogy I would use sometimes when I'm explaining this, which is if you imagine just walking in a straight line, and in theory, if you could do this for a very, very long time, you go all the way around the surface of the Earth and you come back to the point which is just a few meters behind you. Well, clearly you haven't taken the shortest path between your start point and your end point. To do that, you should have just walked backwards a few steps. But at any given time during your journey, you were taking the shortest path between where you were and the point right in front of you. So this big circle around the surface of the Earth really kind of captures this property of if you take a little small portion of it, what you're looking at is the shortest path between the two endpoints. But when you step back and look at the whole object, it's obviously not the shortest possible path to take. So that's a kind of analogy for a minimal surface.
So is there an example of something that people might be familiar with, of a minimal surface or a minimizing, area minimizing surface?
So right, so the challenge is to give a more interesting example that's not a completely flat sheet. And there's one that comes up in real life, or almost comes up in real life, which is a helicoid. So what we call a spiral staircase is sort of something geometers sort of wince at a little bit because it's not really a spiral in the mathematical sense, it's a helicoid. So if you imagine like a spiral staircase, but instead of stairs, it's more of a ramp. So if you trace out with my hand, it sort of just goes smoothly up like that. So it's a nice smooth sheet, a nice surface, and in that shape of a spiral staircase, that's called a helicoid, and that is a minimal surface. So it has those properties I was just describing about the area minimization. That was actually the third, I think, minimal surface sort of ever discovered in the 18th century.
As what you've said has already indicated that, so there may be some practical reason for why people may be interested in such surfaces, because they occur in nature, but you clearly are not motivated by application. So what drew you to this area of geometry as a pure mathematician? What do you find interesting about it?
Yeah, right, there's the sort of, the practical, well, like many subfields of mathematics, the study of minimal surfaces, of course, connects to lots of other areas of mathematics. And the way I came into it was through studying analysis, really. So I was interested in, well, when I was a master's student or looking to start my PhD, I was learning a lot of analysis, measure theory, partial differential equations, and basically looking for a PhD supervisor. And so the professor who eventually became my PhD supervisor is an expert in analysis. I didn't know at the time that really he was using a lot of analysis to solve problems that came from the study of minimal surfaces at kind of a deep level. So I later on learned a lot of the motivating themes for what I was actually learning at a technical level. But more generally, I'd make the point that, I mean, something which doesn't often get conveyed to people outside of academic mathematics is how easy it is to ask questions in mathematics that are completely impossible for any human mathematician to solve. And it's also very common, of course, to ask a question which turns out to be completely trivial and completely easy. Sort of a week later you think, oh, that's just a completely easy question, why was I even thinking about that? So what's the rarer situation is to have a plentiful supply of questions which are just right. And somehow that's when a field starts to kind of gain steam, and that's just seemed to happen with minimal surfaces. So when people first coined the term, they obviously started asking some very innocent questions which turned out to be much deeper mathematical themes than they originally knew.
When was that people first started?
So this would have been near the end of the 18th century. And at some point you can find these letters between, or you can't, I mean you can read them online somewhere, between Euler and Lagrange, discussing these kind of problems about area minimization. And when it first came up, the only minimal surface they knew about was the completely flat plane, like it comes from that example of the area minimizing flat disk. And then the catenoid and the helicoid were found and went from there.
Could you give us an idea of the kind of work that you're doing personally yourself?
Yeah, sure. So as I just mentioned, in the late 18th century, the best mathematicians at the time knew of about 3 different minimal surfaces in total. It took about 50 years before people found any more examples. One of the big lines of inquiry in the study of minimal surfaces is actually finding examples of them. Now, often this is very difficult, as I said before. Sometimes you can't quite find a nice, smooth minimal surface that's a nice, smooth sheet and is very pretty and elegant to look at. Sometimes the best methods you have available produce a surface which maybe has a self-intersection or is badly contorted or pinched or distorted somehow. Now, often, ideally, you'd like a sort of more beautiful theorem at the end which sort of rules out this possibility of your surface looking kind of crumpled and wrinkled and pinched. But sometimes we don't really know how to do that. So we're actually very interested in studying these regions of minimal surfaces where you have self-intersections or distortions or this crumpling. We call them singularities of minimal surfaces. So these bad areas, they retain some of the properties of the area minimization, but it's not a smooth surface. So we can use lots of the ideas and techniques that come from studying this classical setting of minimal surfaces, but often with a lot more analytic machinery to try and understand what the surface looks like close to these regions where it's intersecting itself or is badly contorted. Yeah.
You've only just arrived here, or you've only just started your job as an unestablished lecturer here recently. How do you feel about coming back here? Because you were a student here as well. So how does it feel to be back here and to be working as a lecturer?
Yeah, it's very nice. I think that's it's certainly a very nice place to work.
What's nice about it?
Well, I think most mathematicians, they might not sort of wear it on their sleeve, but if you catch them at the right time and ask them the right questions, you'll discover that they feel very, very passionately about their work. And somewhere like Cambridge is perhaps more so than probably most universities in the world, is lucky enough that the culture and the sort of ethos of the department seems to reflect that very well, that everyone here is very passionate about academic mathematics, and that is the sort of the culture of the place. Not everywhere has chosen to be like that as a department, not everywhere can sort of afford to be like that as a department. But that's very, very nice. And moreover, teaching the students here, of course, is kind of an amazing experience, having taught in a couple of different places. When you lecture here, you sort of really feel like, okay, you're talking to a room full of mathematicians. And some of the courses, and some of the course I've been teaching this term, I took 10 years ago or something as an undergraduate. And I'm lecturing it thinking, wow, this stuff is really hard. This is harder than I remember it. And it's just amazing what they can cope with, and you can really connect with the students over very advanced mathematics. Actually, and it's nice. Yeah.
Okay, thank you very much.
All right. Yeah.